Now we want to look at case number 4. How to find a way that does not rely on the limit. Because if you calculate the limit, it does not exist. Case number 4, it does not exist. Yeah. You get nothing, all right? Yeah. Yeah. Some of you, yeah, if some of you wonder, yeah, what do you mean limit does not exist, right? Yeah, so some students may feel under what situation the limit does not exist. Yeah. Here, I can give you a simple example to see that limit does not exist. Okay, all right. One example, so let's consider this limit. Ratio of two functions. Two functions. The first function, n squared times 3 plus -1 to the n. Second function, n plus 1 times 4 minus -1 to the n. Okay? Let's look at this special case. Yeah. Yeah. The constant part, the plus minus, yeah. You know, that will cause some problem. Yeah. All right. This variable part, you can see, pretty much the same, right? Yeah. N squared over n squared plus 1, you know, yeah, cancel out. Yeah. Yeah. All right. So we only need to look at this number part. Yeah. All right. So let's consider n even odd. Yeah. First, when n is 0, even, the numerator 3 plus 1, denominator 4 minus 1, right? Yeah. 4 minus 1, so 4/3. Then, for odd case, 3 minus 1, 2, denominator 4 minus -1, so 5, right? 2/5. Then, back to this 4/3, 2/5. Two different fractions alternatively. Yeah. In that pattern, in this pattern, if the sequence is this pattern, then no limit. Limit does not exist. Yeah. In this pattern. Yeah. All right? Limit does not exist. Yeah. You know, up, down, you know. This sequence never converges to any number. It does not converge to any number. Okay? Yeah. Yeah. So then we cannot use this limit method. Yeah. All right. So we have to find some method that does not rely on limit concept. Yeah. All right. Now. Oh, sorry. Yeah. Oh, okay. This. All right. Next. Yeah. Let's look at this. We use upper bound, lower bound, using inequalities to compare two functions. Using inequalities, we can also compare two functions. Yeah. So the objective here, we want to go to a different technique. Yeah. All right. So this technique, yeah. Yeah. All right. So when we do comparison, we use inequalities. All right. Yeah. All right. So here, yeah. So here, what we're doing here, yeah. G function. Yeah, G function usually relatively simple function. Yeah. Yeah. So we can get idea of G function easily when we see this. Yeah. But F function sometimes relatively complicated. Yeah. complicated. But we want to use a relatively simple function to help us understand this f function. Yeah. How do we use g function to measure f function? We use constant multiple of g function. Yeah. So the way we use g function to measure f function is constant multiple of g function. Yeah. Okay. Yeah. So then, in that way, yeah, because when we use constant multiple of g function to compare with f function, then we may have the upper bound case and the lower bound case. There are two cases. Yeah. So then we need to, upper bound, lower bound, we need to use two different constants, C1, C2. Yeah. Then C2 multiple of g function is a lower bound of f function, and the C1 multiple of g function is an upper bound of f function. Yeah. So this way you can see we get around the limit. We never need to calculate the limit in this situation. Yeah. But we can do a special type of comparison, right? Special type of comparison. Yeah. Yeah. In inequalities. Yeah. All right. So now, with this new method, we want to define another three asymptotic notations. Yeah. So one of the three we did before. Yeah. So two new plus one old asymptotic notations. All right. Yeah. Yeah. But these three, I only need to explain the first one. Yeah. Because the next two, similar ideas. So we only need to spend our time on the first one. Yeah. All right. Yeah. C.2, define asymptotic notations. Yeah. The first one, big O notation. Yeah. All right. So let's look at the whole definition. Yeah. All right. For a given function g of n, the notation big O of g of n represents the set of functions f of n that satisfy the following condition. Inequality condition. Okay? So what's the inequality condition? There exists some positive constant c. Yeah. So big O will only consider one inequality, positive constant c, and some non-negative integer n0 such that the inequality f of n less than or equal to c multiple of g function when for all n greater or equal to n0. Yeah. Here you can see there is a special constant n0. Yeah. That is important. Yeah. That is useful. Yeah. That is useful. Okay. All right. That means we do not require this inequality hold when n less than n0. N less than n0, it doesn't matter. Yeah. Greater or less, not important. Yeah. But when n greater or equal to n0 constant, then this inequality must be satisfied. Yeah. Then we say f of n is a big O of g of n. This asymptotic. Low here, it is upper bound. Yeah. Yeah. So it's constant c multiple of g is an upper bound of f function. All right. Yeah. Yeah. But sometimes, in calculus, this n0, because sometimes people feel, why we need to mention this n0, right? Yeah, yeah, N0, yeah, yeah, it is useful. Yeah, it is useful. Yeah, we need it. Yeah, yeah. But sometimes people want to get around this N0 notation. Yeah. So people say, yeah, yeah, yeah. All right. So when N is sufficiently large, yeah, so there is a special wording. So when N is sufficiently large, when people say that, then we do not need to mention N0, right? Yeah. So what do you mean N sufficiently large? Yeah. There is some constant N0. Okay? Yeah. There is a hidden constant N0. When N greater or equal to N0, then some condition must be satisfied. Sufficiently large. Yeah. Right? Yeah. So in one of our quiz questions, you can see that. Yeah. I want to mention this wording here. Yeah. Because some of you may wonder, so what do you mean sufficiently large, right? Yeah. So one of our quiz number 2 questions, yeah, I use that same wording, okay? Sufficiently large. Yeah. Your understanding, you use the similar understanding here, okay? Yeah. What's the meaning N sufficiently large? So there exists some non-negative integer N0 such that for N greater or equal to N0, some condition is satisfied. In the quiz, there is some condition. Yeah, that question, some condition must be satisfied, but under this. Yeah. All right. Yeah. So that N0, yeah, although you have freedom to select, yeah, because you can choose that N0, large, small, you have freedom to choose. Yeah. But after you choose it, then it must be fixed. Yeah. That N0 must be fixed. Okay? All right. Yeah. 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 So, and N can grow. Yeah. So N0 must be fixed. Yeah. But at the beginning, yeah, you have a lot of freedom to choose what is that N0. Yeah. All right. If we look at from the graph of these two functions, you can see, yeah, the graph of f, this curve, yeah, but when we multiply some appropriate c constant multiple of g function, yeah, so yeah, because when we multiply, we can raise, lower, moving up, yeah, so we can change, yeah, yeah, but we want to cover it. We want to use c constant multiple to control, yeah, to complete, yeah, cover it from the top. Yeah. So that's the big O notation, the graph. Yeah. But you also see, yeah, this vertical line, this dashed vertical line, yeah, yeah. There exists some line like this. Yeah. After this line, yeah, c constant multiple can control f function. Yeah. But before this line, it doesn't matter. It's not important. Which one higher, which one lower, not important. Okay? Yeah. Before that line, not important. Yeah. So this condition gives you some freedom. Yeah. If this inequality does not hold, you can move this bar right to the right until you reach some point the inequality holds. Yeah. So you have freedom to move this bar. Okay. So after this vertical line, you want to make sure this inequality holds. Yeah. All right. And you can change constant c. Yeah. You can use larger constant c. Yeah. All right? Yeah. So you have some freedom. Yeah. All right. This is our first asymptotic notation. Yeah. But the next two, we use the similar understanding. Yeah. So based on this understanding, so we can understand the other two asymptotic notations easily. Big omega notation. This one we just change from upper bound to lower bound. Okay? Yeah. Yeah. The same similar statement, but this time we use big omega notation, and our condition we use lower bound. Okay? Yeah. The same wording, but inequality. F function is greater or equal to C constant multiple of G function. Yeah. When n is sufficiently large. Yeah. 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 Similar wording. Yeah. But we need a lower bound version. Yeah. All right. Then the graph. Yeah. So this time C constant multiple, the curve is below the curve of F function. Yeah. And also there is a vertical line. Yeah, we need to choose. Yeah. We can move this vertical line, yeah, but we want to make sure the lower bound inequality holds after this vertical line. Yeah. That's the big omega notation, the lower bound case. Yeah. Big omega. All right. Then the last one, our last asymptotic, big theta. Yeah. Big theta asymptotic notation. This time we have both upper bound, lower bound. Okay? Yeah, big theta. Yeah. So we have two constants, C1, C2 constant. 2. All right? Yeah. And the C2 constant multiple of G function is a lower bound of F function. And the C1 constant multiple of G function is an upper bound of F function. Yeah. So the graph, yeah, so this time we have, C1 upper part and C2 lower part. Yeah. Yeah. All right. So that's the asymptotic notations. Yeah. In this class, yeah, so if we look at the previous a few slides. Yeah. Total, we have 5 asymptotic notations. Yeah. So these three big notation, right? Yeah, big O, big omega, big theta, and 2 little, yeah, little o, little omega. So total 5 asymptotic notations. Yeah. All right. But most of the time we use, later in our discussion, so we use 2, yeah, we only use 2 asymptotic notation used the most. Yeah. One is the big O notation. Big O notation, we use quite a lot. Another, second most, big theta. The second most big theta notation. Yeah. And the remaining 3, we do not use much. Most of the time we do not use. Yeah. So we only use these 2, the top 2 asymptotic notations. Yeah. All right. Yeah. Next, now I want to do some examples for asymptotic notations. Yeah. All right. First, yeah, we look at the understanding. First example, very simple. Yeah. We want to show, yeah, m plus 2 belongs to big theta of m. Yeah. All right. Yeah. So for this simple example, there are 2 ways we can do. Yeah. Yeah. Big theta, yeah, because there are 2 different ways related to big theta. The first way, limit way. Limit way, yeah, let's calculate the limit. F function over G function, let's calculate this limit. Limit equals 1, right? Yeah, it's a positive constant. So then we can say F function is the big theta of G function. Yeah. Yeah, but the second one, we need to use upper bound and lower bound. Yeah. All right. The second one, yeah, so let's put the F function here. Yeah. We need to go 2 directions. Yeah. Lower direction and upper direction. Yeah. The lower direction, we want to see what constant multiple of n is less than f function? Yeah, here simple. If we drop constant 2, n is a constant multiple. N is less than n plus 2. Very simple. Yeah. So we get a lower bound. Yeah. And this inequality holds when n greater or equal to 0. Yeah. Yeah. Because we do not consider negative n. Yeah. We only consider non-negative n. All right. Yeah. Here, the corresponding C constant is 1. 1 times n. All right. Then the upper bound. The upper bound side, yeah, now we need to, do some special operation. Yeah, think about n plus 2, because our goal, we want to use the constant multiple of n to be an upper bound of this f function. Yeah, this n part is okay, constant multiple, right? 2 part, we need to replace 2 by another constant multiple. Yeah. Here we replace 2 by n. Yeah. So n plus n, we want it greater than n plus 2, but it is true when n greater or equal to 2. Yeah. Because we have freedom to choose n0, right? Yeah. This 2 is the n0 we choose. Yeah. Yeah. When n greater or equal to 2, that 2, when we replace 2 by n, the result function is larger. Yeah. So we get an upper bound that is 2n. 2n upper bound, yeah, under the range n greater or equal to 2. Yeah. So you can see that's the way we find upper bound and the lower bound. Yeah. Yeah. And in this case, C1 is 2. So we find both C1, C2, and N0, yeah, because both range, we want to satisfy the conditions for both range. So N0 should be 2. Yeah. 2, that both conditions are satisfied. Yeah. Yeah. So when we use the definition way, we need to find these 3 constants. C1, C2, and N0. After you find them, you can make your conclusion. Yeah, f function is in big theta of g function. All right. Example number 2, 2.2. Yeah. Let's practice this method a little more. This time, n cubed belongs to big omega of n0. Yeah. That means we need to find a constant multiple of n squared. That is the lower bound of n cubed. Yeah. Yeah, but this inequality holds. We can see easily, yeah, right, when n greater or equal to 0. Yeah. And we only consider integers, non-negative integers. So always holds. Yeah. Always holds. That means C constant is 1, right? Yeah, C constant is 1. Yeah. Yeah. So that's enough. Yeah. So for big omega, it's enough. All right? Yeah. And yeah, so that's the definition way. Yeah. All right. Next, yeah, we want to, look at this example. Yeah, a little harder. Yeah. All right. This time, we want to find upper bound, lower bound. Yeah. Although the limited way works. Yeah. So here the limited way works. Yeah. But when you calculate the limit here, I want to point out, so there is a simple way you calculate the limit. Yeah. So when you calculate limit n plus 2 cube over m cube. Yeah, yeah. Do not do polynomial expansion here. Yeah, some students may want to expand the polynomial at the numerator. Yeah, so that you need to do a lot of calculation. Yeah, here you can use the limit property because you can you can take the limit inside the parenthesis. N plus 2 over m. Yeah, so here, let me, save some space. Yeah. Cube, put the cube outside, all right? Yeah. In this way, you do not need to do polynomial expansion, right? Yeah. Inside parentheses, the limit is 1. Yeah. So 1 cube, it is 1. Yeah. It's much easier. Yeah. 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 If you do polynomial expansion, it's too messy. Yeah. Although you can find the final answer correctly, yeah, but you need to do a lot of work. Yeah. Not necessary. Yeah. All right. Yeah. Yeah, so then upper bound, lower bound. Upper bound, lower bound, do not do polynomial expansion. The same idea here. If you do, you make it much harder. Yeah. Don't do it. Okay? All right. Let's do the upper bound, lower bound inside parentheses first. Yeah. Let's ignore the cube operation. We only do upper bound, lower bound inside parentheses. Yeah. We did in our first example, right? Yeah. So that's n. See, n plus 2 greater than n, then we raise both to cube. Raise both to cube. Yeah, cube, cube. Yeah, all right? Upper bound is the same thing. Yeah. Upper bound, let's find upper bound for n plus 2 first. Then we raise to cube. All right? Yeah. So here. Yeah. Similarly, yeah, upper bound, yeah, 2n here. Yeah. Then we raise to n. Cube. 2 cube, that's 8. 8 times n cube. Yeah? It's much easier. Yeah. If you do polynomial expansion, you have many terms. You need to estimate all those terms. Too messy. Yeah. Too complicated. Yeah. Although you can do it, yeah, but you need to do too much work. Yeah. So here, it's very easy. Yeah. C2, 1, C1, 8, N0, 2. Yeah. So you can get a conclusion. Yeah. Yeah. All right. Yeah. Yeah. So then, example 2.4, yeah, show that log of m belongs to little o of n. Yeah. Yeah. We did a similar example before. Yeah. Yeah. But here, let me just quickly do this example another time. Yeah. This time, little o, we can take the limit. Yeah. This little o. Yeah. 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 Although discrete variable, yeah, we need to convert it to continuous variable first. Yeah. Continuous variable. Then we can apply L'Hopital's rule because it's infinity over infinity indeterminate form. Yeah. So we need to check it. Yeah. In our mind, we need to check it. All right. Then we can take derivative. Yeah. All right. Yeah. Yeah. So here the base, a greater than 1. Yeah. All right. Derivative x is 1. Derivative log base a of x. That's 1 over natural log of a times a, x in the denominator. Yeah. After simplification, yeah, x in the denominator goes to infinity, the whole fraction goes to 0. Yeah. So the limit is 0. Yeah. Yeah. Then, because this is continuous function, we need to go back to the discrete function, right? Yeah. So we need to, all right. Yeah. So we need one step to go back to the limit 0. Yeah. After we get this 0 limit, let's write another step. Yeah. Because we know when n approaches to infinity, we can take consecutive integers. So we have this limit 0. Then we can make conclusion, right? Yeah. Log function is in little o of n function. All right. That's our third example. Yeah. 4. Number 4. Example number 4. All right. Number 5. Show that n to the d. Yeah, constant. This d is a constant, positive constant. belongs to little of a exponential function, a to the n. Yeah. Here, d greater or equal to 1. A greater than 1. Yeah. How to do it? To answer this question here I want to give you some problem-solving ideas. Here there is some problem-solving thinking, special strategy we need to take. All right. So I use this example to let you practice some problem-solving strategies. I mentioned before. So this time let's practice another time. All right. First strategy. In the original condition, d greater or equal to 1, and d is not necessary integer. D, not necessary integer, just greater or equal to 1. 3.5, 6.7, all fine. But here, when we work, all right. Now, problem-solving strategy. All right, because if d is not an integer, we feel not easy to work on. Because when we work on non-integer exponent, it could be complicated. How to make it simpler? All right. Here, the first strategy. Remember, we can modify our original problem to make it easier. That strategy we used before. When we work on a relatively hard problem, one special way to simplify it, we modify our original problem to make it simpler. Here, what's the modification? We let d be integer. That's simpler, right? We make this assumption. This assumption, we modify. The problem is different. But it is a simpler version of our original problem, right? Simpler version. So this method is used in problem solving quite a lot. Okay? So in your first round, you solve a simplified version of the original problem. That strategy is very important. Okay? So here we apply that strategy. We make it simpler. Here, d becomes integer, simpler. Because when we take derivative, it's easier to work on, right? If it's non-integer, then we take derivative, relatively complicated. So for that reason, because we need to apply L'Hopital's rule. When we apply L'Hopital's rule, we need to take derivative. So we like to make d integers when we work on derivatives. All right. Now let's do the work. L'Hopital's rule. So we consider continuous version of the ratio of two functions, x variable, continuous variable, d. But this time d is integer. All right. Then it's infinity over infinity indeterminate form. So let's take derivative, numerator, denominator. So we apply the formula. The power rule formula. That derivative of exponential function formula. All right. After that, still, infinity over infinity, right? So here we can imagine d, some relatively large number here. All right. Still infinity over infinity. So we can apply L'Hopital's rule another round. Let's apply a second round. So then power rule, formula, We keep doing, so you can see in the numerator, we we have the pattern. The power function part, x to some exponent number, that exponent number keep reducing, right? Keep decreasing, keep decreasing. D minus 1, D minus 2, D minus 3, and so on. Yeah. And eventually, then we will have D minus D, right? D minus D. It's 0. Yeah. The denominator, each time we increment the factor, right? Natural log of A. Yeah. So that part, we increment the exponent number by 1. All right? Yeah. All right. Then, in this case, yeah, because the numerator x power function part becomes constant. Yeah? So, all right. So we can simplify it. After simplification, yeah, we can see the denominator goes to infinity, so the whole fraction goes to 0. Whole fraction goes to 0. Okay? Yeah. Then, when this is the continuous version, then we can go back to the discrete version. So we have n to the d. When d is an integer, positive integer, it belongs to little o of a to the n. Yeah. So for the integer case, we complete the proof. Yeah. But this is a modified version. It's not our original version. After we complete it, then we need to move back to the original version when d is not a constant. D is not a constant. There is a gap, right? There is a gap between d and integer part of d. Yeah? Although d is not a constant, but d has an integer part. Yeah. Then there is a gap between those two numbers. Yeah. All right. Yeah. Here we need to bridge that gap. We need to find a technique to bridge the gap. Okay. All right. Yeah. So now, yeah, imagine here we assume d non-integer. So d non-integer, the ceiling function is an integer, right? Ceiling function of d is an integer. Yeah. Can we apply our result on ceiling function of d? We can, right? Yeah. So we have the so this time, yeah, let's use the x version. X to the ceiling function of d over to the x equals 0. Right? Yeah. So we have this version. Yeah. But here we use the ceiling function of d. It's not the original d, right? Yeah. So our goal, we want to do the original d. Okay? Yeah. There is a gap. Now, let me show you how to bridge that gap. All right. Bridge the gap. Okay? So this limit, let me write it in this way. X to the d, original, over x to the ceiling function of d. How about that? Times x to the ceiling of d over a to the x. Let me split in this way. How about that? Let's split. Yeah, so this x to the ceiling of d, we use it as a stepstone to bridge the gap between these two functions. Okay? Yeah. The first fraction, you put it at the denominator. Second fraction, you put it at the numerator. Cancel out. Right? It's gone. That original. Right? Original, but when you calculate the limit, the first limit, when x goes to infinity, is it 0? The second limit, when x goes, is it 0? Yeah, because we just did it. 0 times 0 is 0, right? Yeah. 0 times 0 is 0. Yeah? So then you get the result for the original version. Yeah. Here you can see how important we solve a simplified version. It is important. And we use it as a stepstone to the original version of the problem. Okay? Yeah. So this strategy, yeah, very important in problem solving. Yeah. So some people call this strategy, because it is so important, then some people give a big name to it. It's called a golden rule. Golden rule. So this strategy, some people call the golden rule of problem solving. So you know how important it is. Yeah. Yeah. So here we apply the golden rule of problem solving. Okay? Yeah. 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 All right. Yeah. So that's this example. Yeah. Next example. All right. Example number 6. Yeah. Log base 2 of n belongs to little of root of n. Yeah. L'Hopital's rule. Yeah. 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 Here, yeah. So, you know, just do the calculation. Yeah. So here I do not explain the, you know, intermediate thinking part. Yeah. So because we repeat it many times. Yeah. All right. Take derivative. Yeah. Yeah. Numerator, denominator, we take derivative. Yeah, so, yeah. Do simplification. Yeah, all right. Now we can see the answer. Yeah, 0. Yeah. 0, then we go back to the discrete version. Then we can write the conclusion. Yeah, all right. Yeah, so, pretty straightforward. Yeah. But yeah, here we want to move to a more general version. Yeah, because this is a special case. Yeah. We want to move to a more general case. So the next example, we want to show more general case. Yeah. All right. Example number 7. This time, the still power function, n to the d, okay, n to the d. Yeah. Natural log belongs to little of power function n to the d, but this d will only require d positive. D positive, that's for any d that is positive, we have this little o relationship. Yeah. How to show it? Let's apply L'Hopital's rule. Right? Continuous version, yeah, yeah, you know, same treatment. First, then we take derivative on L'Hopital's rule. First, derivative. Yeah. Then, do simplification. After the simplification, we get this 1 over d times the original power function, x to the d, but we can see the answer already at this point. The answer is 0. Okay? That means we can go back to the discrete version, we can make this conclusion. Okay? Yeah? Yeah. All right. Yeah. But here, after we complete it, yeah, because this d, only positive, not necessarily integer, any positive number, it is true, it's correct. Okay? All right. Then I want to talk about 2 of our homework questions, number 8 and number 10. Those 2 questions related to the results we just discussed here. Yeah. So let me make some comments on those 2 questions. All right. First, yeah, let's look at this little d case. Yeah. D, any positive integer. So we have freedom to choose this D number, right? Yeah, we have freedom to choose D number. Now, let's apply our freedom to choose a special D number and compare these two functions. Yeah. Compare one natural log function and another power function, yeah, power function, but we make this D very small. How about that? 1/millionth. 1/millionth. Yeah. That D is extremely small, right? And to this very small number, this power function, how can this power function compete with a natural log function? Okay? How can it compete? Right? Yeah? But if you look at the result we just proved, you know which one is larger. Yeah. Which one? So here you can see many students, they use their intuition to do the comparison, right? Intuition. But when you use the intuition, this power function, based on your intuition, very extremely small. Extremely close to 1, right? Yeah, because you take 1/millionth root. 1/millionth root. Okay? So small. Yeah. But when we do comparison, we consider when n is very large. When n goes to infinity, yeah. When n relatively small, which one is larger? Not important, right? Remember our vertical line. Before that vertical line, n0 vertical line, which one is bigger? It's not important. Yeah. We only want to look at the behavior when n is very large. Here, you need to look at when n is very large, that situation. Yeah. So you can apply this result here. Okay? Yeah. All right. So that is one example. Another example, this result. Okay? Yeah. D and integer, D could be very large, right? Yeah. Yeah. All right. A, we only require A greater than 1. That's good enough. So exponential function. So when we compare, so here we apply this result. Okay? So for the first example, we apply this result. For second example, we apply this result. So let's compare. Now, all right. D could be very large, power function, so n to the 1 million. How about that? It's a very large power function, right? Yeah. 1 million exponent. Yeah. Yeah. Growing very fast. All right. Then we compare it with our second exponential function, 1 point, greater than 1. 0, 0, 0, many zeros, 1 to the n. Okay? All right? Yeah. Which one grows faster eventually? Okay? Yeah? All right? So if you make a decision based on intuition, so then you may feel the first one is much larger, right? Because the base is very close to 1. Okay? How can this function, you raise to nth power, how can this function eventually overcomes this big power function, right? How can that happen? Okay? Yeah. We have this result here. We have this result. We prove it. We prove it. Okay? Yeah? All right? So these two examples tell you your intuition many times may not be reliable. Yeah. You get illusions. People get illusions. Yeah. Their intuitions are wrong. Yeah. Yeah. It could happen. No matter how smart you are, your intuition could be wrong. Okay? Although we need to use our intuitions. Yeah. It's important. Yeah. We need to solve many problems based on our intuitions. Yeah. But sometimes your intuitions could give you the wrong answers. Yeah. So for these two questions, you should be very careful. Yeah. Because our results may against your intuitions. Yeah. Yeah. So you need to think twice, think carefully. Okay? Yeah. I remember once one student, yeah, so one student does not believe, this function is greater than that function. So that student used some online graphic calculator to draw graphs to compare. Draw graphs. Yeah. The graph of this one very flat. Yeah. Very close to 1. Yeah, because you take root, so large root. Yeah. So the very, very flat. Yeah. Yeah. And the graphic calculator has limited display area, right? Although you can drag, yeah, but you can never see the end. Okay? Drag it, yeah. So that student showed me, yeah, the graph tells us, this difference, yeah. But the problem is, your graphic calculator is online graphic calculator very limited. Okay? Yeah. You cannot see infinity, right? Yeah. Yeah. You cannot see infinity, all right? Right? You have a lot of limitation you cannot see. How do you know? Yeah, something different could happen at the very far end. Very far end. You cannot see it. Yeah. But it occurs. Okay? Yeah. All right. Yeah. So that's the 2 questions of our homework assignment. One question number 8. One question number 10. All right. Yeah. And then there are another 3 questions. Now, other than these 2 questions, another 3 questions related to the materials, topics we studied today. Yeah. About inversions. Yeah. So as I remember, there are 3 inversion questions. Okay? Yeah. 3 questions. So you need to work based on the inversions. Yeah. Understanding. Yeah. So total, there are 5 questions related to today's lecture in our homework assignment number 1. Now, so among those 25 questions, yeah, there are 5 questions related to lecture today. Yeah. So, yeah. All right. Yeah. And this assignment, homework assignment number 1, quite challenging. Yeah, quite challenging. Yeah. So you need to, although you have plenty of time, okay, so you have a little less than 2 weeks. Yeah. A little less than 2 weeks. Yeah. Plenty of time. But you need to, do not waste your time. So you need to, work as early as possible. Yeah.
Do you write everything on the paper?
Yeah. Look at my instructions. Yeah, not everything on paper. All right. First 10 questions, then multiple choice. Yeah. All right. Then next 10 questions, yeah. You only need to put your answers, but if you can put your main work, you can earn extra credit when your answers are wrong. Okay? Yeah. So you don't need to put the details, but try your best to earn extra credit. But only the last 5 challenging questions, you need to put all the details. Yeah. So that's the difference. That's the difference. Yeah. Okay? Yeah.
What is it? Is there like multiple choice, but don't need to write down the answer on or note sheet or notebook, or do you need to print the stuff?
You can write on this. Yeah,
Oh, okay.
yeah. You don't need to print. Yeah, yeah. Just let me know clearly which one you choose. Yeah.
Okay.
So that information. Yeah. So I do not need to use, the format. Format not important. Yeah. If I can recognize your handwriting, so no problem. Yeah. Yeah.
Or we can just add it as a PDF.
I like the PDF because when I do grading, so I need to use the PDF file to grade it. Other files, I need to do conversion. Yeah, because some students use many different formats. I need to do conversion first. Yeah, PDF, I do not need to do conversion. I can grade directly. Yeah. All right, that's it. Yeah.